All right. Now, I haven't rehearsed anything. I have put some things on the board, but this video is about what a graphing form is. Um, and hopefully I'll say some things that you can connect with and that make some sense. We're going to look at the graphing form of a quadratic. We're going to analyze it from numerical standpoint and geometric primarily. And again, the purpose is to get a little better feel for what a graphing form is, which is simply a calculation written, which allows you to see the shape of a graph and interpret the salient characteristics. And I'm using the word salient because we do word of the day and then we repeat it, and salient means most important. So we're going to look at the most important aspects of what's taking place as we design these, as we look at these calculations, especially from a geometric perspective. I think that's the most important. And then the numerics support the geometrics and gives you a better feel for what you're looking at. So here's the quadratic. Y equals ax squared plus bx plus c. There's three terms. And they're being added up, which means that we have a y value coming out of ax squared. You know, we can see the y values for ax squared. We have y values coming out of bx. So if I pick that x, my y value is negative. It has certain size to it. And I'll start drawing a couple of these with hopefully a red marker. And then we have a constant function. And I'm not assigning any values to these. I'm not saying if this is x squared, 2x squared, or 3. It's certainly positive. The a value is positive. All right, so let's start here. All right, and let's talk about that altitude, which is shared by ax squared and bx. Sort of, well, if I drew it a little better, it would be shared. And so let's pretend it's shared. So I really have two of those, one coming from the linear term, one coming from the quadratic. So I'll double that in size. And then I'll add this constant, which is actually the same size. They all intersect there, right? And so I would end up here somewhere, and my graph would produce that y value. I put a little X marks the spot there. All right. What happens if we added these three here? Well, these two are 0. Whatever that is, well, my quadratic is going to go through. I don't have a good marker here, so I'm going to change that one right away. Hopefully it's something I picked that works. All right, so my quadratic passes through these two places. And we might want to talk about rates of change immediately here, right? Because I'm going to support it with geometric work on the other side of this board momentarily. But the quadratic's flat at the vertex, and there's a geometric reason for that, and we'll look at it. The linear function is increasing at that rate, and the constant is flat. So if I added those three rates together, there's no contribution here, right? Linear, you know, if this was going up or going down, that's the slope of a line, right? So this is the slope of 0. So rate of change is 0, rate of change is 0 plus whatever this rate of change is, means that this function is actually going up at that instant right there. And then the question is, what's happening on the other side, which is more interesting to look at? Well, I have a y value here that is that length, which is negative. I have a y value there, which is the constant contributing. And I also have the y value of the quadratic. So I really have a positive that's that size and a negative that's that size. It looks like this one is slightly bigger than that one, which means that I am actually adding those up. I'd be here. I'd be somewhere just above the x-axis because this positive is slightly longer than this negative. Remember, y values are measured with vertical lines. So that means that I'm coming down, but I'm starting to come back up again. And the question is, where does that happen? Okay, but that's three graphs. A graphing form, you know, that's if you're studying quadratics, that's the graphing form for a quadratic. I see two terms. I see you know, in the terminology of transformations, I teach writing functions from a point if there's a pattern, then we should be able to describe numerically how things change from that pattern, and you can. Those are the 10-second calculations. But folks talk about transformation. So if I have a shift, either left or right, then I'm on the x-axis with the first term, quadratic if the a term is positive, and a constant, kat, cat. If I add those together, it's like a shade, just pulling this down that many units. Each one of these y values is simply going to be pulled down by that negative amount. And I'm going to get a graph that looks like that. It's easier to process two terms visually than three. My favorite is the cubic, and there's plenty of stuff on the YouTube channel to look at that. Okay, but I really think that we should do away with mx plus b. We should write ax plus b. That's two terms. And I think we should get in the habit of writing it as one, learning to factor the a out, a times x, ax, and a times b over a plus b. And then, of course, that morphs into, with the quadratic, x plus b over a squared plus, well, I guess I wrote it here, plus the y value at minus b over 2a. Those in the cubic, important place for a cubic is minus b over 3a. So there's something very interesting to study there from a geometric perspective. But we're going to concentrate now on just the quadratic. All right, so what have we established? We've established that if I write y equals, say, 3x plus 2 squared plus 5, then I have a cup shape up, and I can see the vertex at negative 2, 5. And we're going to talk about the significance of negative 2 from a geometric perspective when I turn the board over. So I can see the vertex here. Now, if I multiply this out, I'll do it real quick. I get 3x squared, 4 times 3, 12x. If I square this, I get 4, 12. Take away 12 plus 5 minus 7. Okay, so that should be the three terms I'm looking at. All right, can you see the vertex from that? If you put it in this form, I can't. All right, but if we put it into graphing form, okay, I can visualize the graph. That's what a graphing form is. So a cubic, which has 4 terms, if you put it in graphing form, you've got 3, and a cubic is the interplay of something cubed and some linear function and some constant, which we can ignore the constant really, right? All that does is, like a shade, move the graph up and down. And now I can see that the interplay of this gives me a graph that looks like that, because this at the point of inflection takes over, but eventually a cubic has more numerical strength, which turns it up and turns it down. And you can look at some of those videos to explore that if this starts to make sense to you. Now let's try to make it some sense for you by looking at the quadratic, which is easier to work with. All right. So with the help of modern technology, I have drawn a square area in black. And let me get this advanced technology here, Scotch tape and cutting on a cutting board, a piece of paper. And what I'm going to do is I'm going to put this white square and superimpose it over the black to the best of my ability. Oh, it's up. Modern technology tells me to turn it the other direction, so the Scotch tape actually works. There we go. Now I've already done that. With, oh God, yes, I made it red. I made these squares red. So we can have black minus red, the red and the black. Famous novel. I don't know if I pronounced Stendhal's name properly, but it's about Napoleonic era and the church in France. It's a great read. I recommend it. Good read for you. And so here's the red area. All right. All right. So we're looking at this geometrically. I hope that shows up a little bit. And I've got a 2 by 2 here. Over here, I got a 3.001 and a 3.001. Here, I've got a 1.001 for the black, which is underneath the red. All right. So what I basically am doing is trying to get a numerical feel for an instant as to how quadratics are changing. I'll support it with numerics here in a second. Here's a half by a half. And what I'm standardizing here is 0.5 gets us 0.25 for area, working decimally, and then I'm gonna look at 0.501, and I'm gonna square it. And those numbers are there, and you can pause the video and think about that a little bit. It's easier to work with the integers. I'm gonna do that in a second. So what I'm really doing is the black area minus the red area, even though I'm losing, maybe I'm not, the red area. And so that's the change in area, which we're gonna think of as y2 minus y1 over the longer dimension, which is the 0.5001, in this case, 1.001. I'm standardizing the change in y. The change in the side length. I'm standardizing. And I'm making it really small. But I'm still just doing the definition of slope, except I'm taking a microscope and zooming in. And a small change. And if I do, there's a nice pattern here. Because this one, right, if this is 0.001, that little black, and this is 0.001, that little black change in dimension. And if this one is 0.001, that little change in dimension. And same thing over here. Here's the numerics that support it. We get ourselves a nice little pattern. 0.006. I'll do it once over here. The change is basically those first three decimal places. There's a little bit of error on the cusp for each of these, but it's basically 0.006 divided by 0.001. And that sure looks like a 6-to-1 rate of change at that instant. So at 3, I might get 9 units of area, but I'm going up roughly at 6-to-1. And if you pause the video and look at these, at 2, we get a 4-to-2 ratio. At 1, we get a 2-to-1 ratio. So at 2, I get 4 units of area, and I'm going up at 4-to-1. At 1, I get 1 unit of area, and I'm going up at 2-to-1. It sure looks like I'm doubling the x value, and I'm starting to get a little bit of what's called a slope field. A little field. Just a little field. And I'm not doing anything other than working with algebra 1, technically. I'm not sure I believe in those demarcations. Math is math. Right? All I'm doing is comparing the change in area. The black, right? I can pull this back. There's a black square area. 3.001 times 3.001. There's my new area. I've got a 3x3 in the red. 3x3, and I'm looking at the change in area, and the change in the side length. Okay, and so dimensions. This is all about dimensions. I personally think 90% of high school math is about rectangular relationships. Right? You think about how you add up the area under curves. Long lines really have little width and height. It's rectangle. Okay, getting ahead of myself here. Okay, so where do I want to go with this now? The graphing. Okay, lost my train of thought. I shouldn't have interjected that. Okay, so what do we do with? I suppose I've shown you what I really want, but let's actually do a problem, and let's get a graphing form. That's what we're practicing in class. So I have a marker here that you can see. So how do we write y equals 3x squared plus 30x minus 7 in graphing form? Well, the a term is given, we just take it. And we do really x minus h, so we have to find h, which is the average of the roots, right? If you have roots at 3 and 7, for instance, then what's that x value? That's 5, right? 3 plus 7, 10 divided by 2 is 5. So it's the average of the roots. For a cubic, the average of the roots is minus b over 3a, and that gets you the x value of the point of inflection. So minus 30, that's minus b, over 2 times 3 is 6, is minus 5. And so I'm going to write x plus 5 squared. Okay, and then I'm going to come back to this and explain this a little more. And so that's going to get me 75. I don't want 75, I want minus 7. So I gotta subtract 75 minus 7 should be minus 82, I believe. So what's my change in x from minus 75 divided by 3 squared, five, never mind. Let's go look at the geometry again. So, and these numbers, all right, so I went from 6 to 4 to 2, and when I do a half to 1, it sure seems like 6 to 4 to 2 to 1 is headed towards what? No change. Where do we get no change? Where do we get a flat slope field? Right? Because a quadratic, if we do a slope field, eventually has a moment where there's no change. When does that happen? The 0 by 0. It's pretty hard for me. If here's a square, and what I'm doing is I'm trying an x distance and an x distance. Here's my square again. If I'm doing an x and an x, 1x, 2x, 1x, 2x, 1x, 2x, 0.001 each time. What's happening to the size of my square? All right, well, look at the size of the black here, from the bigger to the smaller squares. Right? And I'm trying to standardize it with the width of the pen. Well, this change, the black ink, is not as much as that black ink on the board. Where do I get more black ink on the board? The bigger the square. So therefore, if there's change, I'm going up faster here. I think we can see 0.006 is bigger than 0.004. New area. Accumulating. That's integration in calculus, by the way. And each one of these layers is really imitating a derivative. Okay, something you'll hear and see in the future, but no reason you can't understand this from a geometric position at your age. I saw an MIT guy teaching kids in 5th grade some of these fundamental calculus concepts. Want to introduce them earlier so that when you get to that level, you have a better chance of processing. That's why I'm doing this. So when do I get no change? When whatever's inside here is a 0. Okay, so why am I writing this? Because the change occurs, no change occurs when I put a minus 5 in. And that's where our graph is going to be flat. Okay, and saying okay a lot here. And so this is a graphing form. It's harder to see what's going on here, but when I write this, I have a cup shape up. I have -5 giving me -82, right? Because I'm getting rid of the geometry here. And then I know my y-intercept is 0. What is it? 0, -7. And then we've been talking about what in class? The A term of 3 comes from rise over run squared. Okay, so what's the run? The run is -5 to 0. But what am I doing with that run? I'm squaring it. So what's the squared change from -5 to 0? That's a change of 5 units, but the squared change is 25. So the squared change is 25. Hope you can see that. Yes. And what is the change from -82 to -7? I'm going up 75. I'm going up 75. And what's 75 divided by 25? 3. Must be a coincidence. Okay, so these are things you got to think about, right? And you got to start the conversation. So I'm starting the conversation here. Well, actually, I started it with my class 3 weeks ago, but I'm keeping talking about it. Why? Your brain has to neurologically connect with the concepts. That doesn't happen overnight, right? So you hear about it again. And if you're not in my class and you're studying this, then maybe you play it again tomorrow. And if you do, the things I just said will make a little bit more sense. And then maybe you take 2 minutes and play it again 3 days from now. Makes a little more sense until the lights go on. And then you're understanding this stuff at a geometric, numerical, and symbolic perspective. My favorite is the cubic. And if you want to see how a cubic changes, here's a cube. And let's say it's a 2 by 2 by 2. And then I'm going to make it a 2.01. new volume. I just put more volume on that cube. I hope I'm saying the right things. And so that's the derivative. And what are you looking at? A square, and another square. I see three of them. And in calculus, we would say the following, and I'll end with this. We would say y equals x cubed, the cubic. So the change in y over the change in x, let's say that I take a 2 by 2 by 2, and then I make it a 2.01 by 2.01 by 2.01. Well, it turns out a 2 gets you 8, and a 2.01 gets you, let me remember this now, gets me 8 point, let's see, 3x squared, so x squared is 4 times 3 is 12, 012, 3 times that is 006, 001. The geometry of that is fun to think about. Okay, so the cubic looks like the following, and I'm 2 minutes away from being done. The cubic graph looks like this. Oh, looks like it's flat right there at the point of inflection. Why? Pause the video and think about it. Because what happens if the size of the cube is 0 by 0 by 0? What would the derivative look like? I wouldn't be putting much, right? I wouldn't put any layer on it. Pretty hard to draw a layer of volume when the cube doesn't exist. And what is this layer? It's the surface area. Right, that's what it is. I'm really putting surface area with a little bit of what? A little bit of a third dimension, and that third dimension is how thin I can make this piece of cardboard. Right now, I'm representing it by 0.001, 2 zeros and a 1. What if I were to make it 0.000000001? Well, then my 2.00001, that has 5 decimal places, becomes 8.00012. 00006, 00001. That's still the change. The other stuff is, if you can draw it and think about it, overlapping in places that really don't affect the 3 sides here, the 3 squares. All right, I'm rambling. All right, but what's the rate of change at 2 gets me 8 units of volume? I'm really going up at 12 to 1 right there. So if I drew a tangent, the slope of that tangent would be going up 12 to 1 at that instant. Okay, some thoughts, some concepts that I want you to hear before you get to calculus, because most people drop out of calculus because they just work mechanically and do the formulas and go, well, what am I looking at? What's going on? Right? So I think you got to start these things earlier. Right? If I was teaching you baseball, I wouldn't, I don't think I'd hide how to turn a double play till you were in high school. Right? You start working on it at a young age. You start developing your skills. And I think math's the same way. You develop your concepts from simple little manipulatives. And then you can extrapolate later on to more difficult situations. All right, I'm hoping that helps somebody. And if not, at least the conversation has started. All right, gonna sign off. And I'll call this, what is a graphing form? Ta-ta.